Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we'll be looking at GCSE chemistry, calculating reaction rates from graphs. So last time we talked a bit about rate of reaction factors, how there are certain things that increase the rate of reaction and decrease the rate of reaction. But now we'll be looking at the quantitative stuff, at the real deal. How do we actually calculate the rate of reactions from the reaction graphs? So without further ado, let's get started. So here we have, this is our typical reaction graph, and in the y-axis we have amount of product, and in the x-axis we have time. So as the reaction progresses, we are getting more product, and then once the reaction is finished, we are not getting any more product. So the line flatlines. So if we get a flat line, that means the reaction is finished, as we discussed in previous videos. So that's our typical reaction graph, nothing special about it. But how do we actually calculate stuff from it? So first of all, let's have a look at the mean reaction rate. How do we calculate the mean reaction rate? So we have this reaction happening, it has finished, and now we want to see what was the mean reaction rate. So in order to do that, the rate of a reaction is signified by the gradient of the line. The more steep the line is, the more product you made in less time. The more shallow the line is, the less product is made in more time. So the gradient of the line signifies the rate of the reaction. So if we were to calculate mean reaction rate, we have to take form like a triangle to do that. So if we want a mean rate of reaction from the entire reaction, then we will form a triangular, this kind of a triangle, I call it. It won't be a perfect triangle because it's a curve, but this kind of a triangle from this graph. So the reaction finishes when it flatlines. So the reaction it kind of finishes about here. So that's our one point of the triangle, and the reaction started here at the 0 point. So that's kind of our other point of the reaction. So here we have a change in the amount of product, so change in y, and here we have a change in time, so change in x. In other words, to remember this, I often use, here we have rise, and here we have run. And to calculate the kind of a gradient of this line, we simply have to do rise over run. So in other words, change in y divided by change in x. So here we would simply divide the amount of product by time that it took to create that amount of product, and we get the mean reaction rate, the average reaction rate, because it's the curve, so the actual rates differ at different points, but the mean reaction rate would be the result of this. Now, the important thing to consider here is the units. What are the units here of the rate of reaction? Well, it depends on the units given in the graph. So, for example, if the time was given in seconds and the amount of products would be given in moles, then the reaction of the reaction rate, since it's rise over run, so change in y divided by change in x, so we are essentially calculating here moles made per second. If the time was hours and here we would have moles, then we'll be looking at moles per hour. That would be our reaction rate. Sometimes we would not be looking at moles. Sometimes we, for example, look at the volume of a gas released. So we would do, for example, centimeters cubed per second. So the units that you use for the reaction rate are very much dependent on the units that are presented in the graph. So that's how you do mean reaction rate. Now, what if you didn't want a mean reaction rate of the entire reaction? What if you have a specific points where you want to do the mean reaction rate? So what if we wanted, say, I don't know, maybe here let's call it 20 seconds and here 50 seconds. So mean reaction rate between those 2 points. Well, in that case, the method is the same. You create this sort of a triangle and you do change in y divided by change in x. The core concept stays the same. However, what changes here is the values you're going to use, because here you look at the change in y. So not the total amount of product anymore, just the change in y. So what amount of product does this correspond to? And the change of x in x, so what amount of time this corresponds to. So not the total time. So the concept stays the same. You just have to stick to the concept and you will get the right answer. Now, what about if we are looking at the reaction rate at a given point? So the concept will be very similar here, but we'll achieve it differently. So what do I mean at a point? So for example, we have a point here, point A. And we want the reaction rate, we want to get the reaction rate at that one specific particular point. We don't want the mean reaction rate, we want the reaction rate that's happening at this one particular point. Now, to get the exact value is actually pretty difficult, but as far as you are concerned, the way you need to know to do this, it kind of approximates the rate of reaction here. It's pretty accurate actually. So this is the method that you're going to be using for this. So the first thing we have to do here is we are working on the same concept. So we need to have a change in y and change in x. We need to have a rise over run to divide through. But we are looking at a single point. So how do we do that? Well, we do that by drawing a tangent line that we will use to approximate this. So we will draw a tangent line. Now, the tangent line is kind of a line that goes and touches that point. It's a straight line that will touch the point and then it will carry on. And it wants to match the sort of the angle that this particular point is at. And the way to check that is that the tangent line, if we draw, let's approximate the line. So I am gonna try and do this without a ruler. So here's our tangent line. It's not straight, I don't have a ruler on hand, but the point is, here we have our tangent line, and the idea is that the perfect tangent line will have equal angles on both sides. So this angle will be the same as this angle. And that would be a perfect tangent line. As you can see, this line probably isn't that perfect, but the perfect tangent line would have equal angles at both points. But in either case, we have our tangent line. And now we need to, again, do the same thing, the same concept. So we'll look at so let's draw up a triangle. Now the bigger the triangle, the less error you are introducing. So let's make this triangle pretty big. So for example, let's go from here to, let's extend that line a bit. And let's go like this. There we go. And that's our triangle. And now this becomes our change in y. Change in y. And this becomes our change in x. And we are doing the same here. We are just simply dividing rise over run. Change in y divided by change in x. So rise over run. So as you can see, it's a very similar concept. It is pretty much the same concept. It's just that if we want the reaction rate at a point, the challenge here is to draw the tangent line. And now I drew a triangle like this. Because this is a straight line, whatever triangle you use, wherever you put that triangle, you should get the same answer because it's a straight line. It has a single gradient. So whether I do a triangle maybe there, whether I do massive triangle across here, whether I do a triangle like this or even triangle like that, you should get the same answer if you're calculating gradient correctly. So the concept, so that's what I'm trying to underline here. The concept is the same. You for mean reaction rate, you just get a point that you're interested in, you draw up that triangle that gives you change in y and change in x, and you do change in y divided by change in x. Same with the reaction at a point. The only extra bit is you actually have to draw a tangent that represents the reaction rate here at this particular point, and then draw up a triangle that will give you again change in y and change in x, and you do change in y divided by change in x. So that's how you calculate the rate of reaction. And don't forget the units, pay attention to the units here because those will be your final units for the rate of this particular reaction. So this is it for today, guys. Thank you very much for watching my videos. I really appreciate when you guys watch my videos. I hope this video helped you. If you think this video helped you, give me a thumbs up. If you want to see more videos like this on GCSE chemistry, GCSE biology, physics and maths, as well as some biomedical science videos on university level, don't be shy, hit the subscribe button below. Thank you very much again for watching and see you next time.